Hello everyone, welcome back. Today we're continuing to exploring closed loop optimization. In particularly, we're going to zoom in to the topic of how to select the next experiment. We're going to discuss how to design experiments under limited budget, what's the role of an acquisition function, and how do we balance exploration and exploitation as we design the next experiment. Let's dive in. So previously, we've been talking about we can build a surrogate model using Gaussian process regression model. In particularly, we can predict the outcome of our experiment with uncertainty. So here on the left side of the screen, you see this is the Gaussian posterior mean and the uncertainty estimates after 2 points were taken, so 2 observations. On the right side, we see what is our surrogate model look like after 3 data points were collected. So at this point, you may be thinking, well, how do we decide that the pink triangle point, the third point we decide to collect our data, is the right one? Or why do we collect data at this specific temperature? How does it help to build a better surrogate model or help with our prediction? So these considerations are exactly what we need as we try to design the next round experiment based on the information we have from a surrogate model. So let's think about the problem formulation of a Bayesian optimization framework. So imagine, again, we are a thin film fabrication engineer. We are trying to find the optimal temperature that allow us to achieve our desired property of interest. This property of interest can be the toughness of the thin films we are making. It can be like the defect level we are interested in, like minimizing, and so on and so forth. But typically, like as we try to design the iterative learning of our experimental workflow, so we are thinking about the optimal experimental design. So we are not randomly selecting where do we take our next data point. We are trying to select the conditions that provide the maximum insight while also keeping the experimental budget low. We are trying to find the insight of our parameter space with minimal number of experiments. Or it can also be like the shortest time and also like in the cheapest fashion. So as we formulate our study as an optimization problem, we often need to think about our objective function. So an objective function is basically like our goal of our optimization. So in this case, let's say we are seeking to understand like how our input x relates to our function fx, but in particularly, we are trying to find the x that actually gives the smallest y, or smallest property of interest. So imagine this is our goal. So from there, we can start to design experiments that navigate this parameter space and allow us to achieve our goal, which is to find this x, give us the smallest property of interest. Maybe it's the defect level we are trying to minimize. So now, let's say if we already taken 5 random points at this stage, and one thing we should notice is that in reality, often our observables can be noisy. So although the true values, so imagine we have a true function describe the relation between our property of interest and the temperature, it's this red cross. But when we actually make an experimental measurement, we'll have noisy data, so they may slightly deviate from the true value. So in a real life experiment, we don't see this blue curve. We don't see the red cross. We only see the yellow points, and these are the measured property of interest from our 5 sampled data points. So from here, of course, very excitingly, we can build our Gaussian process regression model as our surrogate model. And in this case, you see we have the orange line showing the predictive mean, and also we have the uncertainty estimates like from our Socrates model. One thing, like when we thinking, this is really nice. So now we need to decide where to sample for our sixth sample. Of course, like we need a rule to guide such design experiment. And acquisition function is indeed a rule to score potential experiments using our Socrates model. So behind the scene, the acquisition function is the decision engine in our closed loop optimization framework. So typically, when we are thinking about like choosing what acquisition function to use, we would consider exploitation, which is to focus on the current best results. So in a way, if we already have like a region in our parameter space shows like pretty good results, and so we may want to just sample around it, maybe because this is close to our best results. On the other hand, we also have exploration. Exploration is really to search the unexplored region. In other words, the region with high uncertainty, because this means like we can boost our chance to find in an unexplored region some really good results. So on the top of the slides, you see like what is the Gaussian progressive regression model after we sampled 5 points. And maybe the first attempt is, let's ignore the uncertainty. And let's just have an acquisition function of sampling the conditions that with the smallest possible posterior mean or smallest possible property of interest from our current understanding. So you can see like the acquisition function value would rank for different temperatures what is the highest acquisition function value. So the highest means like, oh, let's just choose this point to sample next. And so, but we have a ranking. And then by using this acquisition function of choosing the smallest posterior mean, and you can see the sixth sample has been sampled, and then this updates our Gaussian process regression model with the additional information of the sixth sample being sampled at this star location. So this is really kind of intuitive, but it comes with a problem. So you can see in this region where we are currently keep sampling, this is a minimum, but it is not a global minimum. If we know the true function, we would know this is a local minima. So we actually want our acquisition function gradually or even quickly lead us to the global minimum. So by choosing acquisition function of only considering what is the minimum, the posterior mean we get, and ignoring the uncertainty, we are not encouraging the exploration of the unexplored region, which means we may miss the true global minimum of this parameter space. So with that in mind, a lot of the state-of-art Bayesian optimization frameworks actually choose acquisition functions that balances the exploration exploitation. A popular acquisition function is called expected improvement. So this is an acquisition function that chooses the next experiment by maximizing the expected amount of improvement over the current best observation. So conditions that with good predictions, so it has the expected improvement, and also with a high uncertainty will be chosen. So in this case, you see on the top, it's the same initial Gaussian process regression model with 5 samples, and with this expected improvement acquisition function, it gives the ranking of the acquisition function value, and the 6th sample would be sampled at the star position, and then we update the Gaussian process regression in a similar way as the previous slides And this gives us an updated Gaussian process regression model. And you can see using this acquisition function, we can keep sampling. So in fact, this is the Gaussian process regression model, our saw-grid model, after 7 observations. So in this case, we already sampled 7 data points. And we continue, and you see it's like using the expected improvement acquisition function. This is what it would look like after we've done 10 observations. So in a way, 10 samples. Continue, and this is the results. Like after a few rounds of the sampling and making predictions, sampling again. So after 20 observations, this is what it looked like in terms of our saw-grid model. So you can see now we are actually pretty close to the true function of this this parameter space, and you can see this global minimum. We start to sample multiple points. So you can see it's like in this case, like we're getting closer and closer to the true functions, and we are also like getting closer and closer of finding the global minimum of this function. So expected improvement is one of the examples of acquisition functions. There are definitely like a number of acquisition functions like people like have been using like a lot. So another very popular choice is the probability of improvement. So again, this is an acquisition function that balances the exploration and exploitation. But in this case, like we are selecting the next experiment by maximizing the probability of achieving an outcome better than the current best observation. Similarly, upper confidence bound is another popular acquisition function. And this allows us to balance the predicted mean and uncertainty by adding a weighted uncertainty term to our surrogate mean. So like in this case, like you see, it's like when we are sampling 7 data points, different acquisition functions leads to like a little bit different like sampled points, and this becomes like more obvious. Like you see after 20 observations, like both the acquisition functions shown on screen, they all get like closer to like the true function we are interested in. But you can also see like when you are designing your own problem, benchmarking and comparing different acquisition functions would help you to find the engine of decision making, like in the way that some of them are faster in converging, some of them are like gives like a more accurate saw-grid model to model the parameter space of interests. So like behind the scene, different acquisition functions definitely comes with different mathematical formulations in terms of how they are encoded. So like I recommend like this book shown on the screen, the Bayesian optimization. And in this book, there are detailed mathematical like formulas and also explanations in terms of how to build your own Bayesian optimization framework with different choices of acquisition functions. So with that, I also want to like share like a broader context when it comes to selecting the next experiment. So in this lecture, we've been using a one-dimensional optimization as an example to show how like we can use different acquisition functions to select the next round experiment. But certainly, like the optimization strategies going beyond one dimensions. So on the screen here, we see like an example. We will have like a two-dimensional optimization space. We're interested in optimizing the temperature as well as the annealing time. And here, like you see, is like the property of interest is shown on the z-axis, and this is the true function. And then as we start to sample, and we start to update our Gaussian process regression model, so this is our predicted values of this parameter space. And in this two-dimensional space, you can also see like we can use Bayesian optimization. And in this case, like I used the expected improvement as example, and you can see the path of Bayesian optimization choosing different points and gradually it leads us to like the minimum of this function. At the same time, you can also visualize the uncertainty of like the predictive model. And in this case, you see which region we've sampled a lot of data points, we're most certain, and which regions we have not like sampled much yet. So this is definitely like something to keep in mind. We can select an experiment when we are thinking about optimizing in a high dimension space. We can like simultaneously optimize our like process or like our materials when we're considering multiple like input parameters at the same time. With that, thank you very much for listening, and see you next time.